Just going to tell you that our advertised speaker for this evening, Justin Kinsella, he's attending a surprise family event that he found out about earlier. Well, as he put it to me earlier, we have now upgraded an upgraded presenter in HTL's lead engineer, Jandré Oosthuizen. Jandré is their Director of Materials and 3D CP Operations, and that stands for 3D Construction Printing. Jandré, he's a materials engineer who holds a master's degree in civil engineering from Stellenbosch University in South Africa. And with a singular focus on 3D construction printing, Jandré expertly marries the principles of materials science with a commitment to innovating the 3D construction printing industry. So we're delighted to have Jandré with us this evening to give an insight into what has been happening in the field of 3D printing of houses. And so, without further ado, I'd like to hand you over to our speaker for this evening, Jandré. Thank you.
Thanks very much, Francis. Thanks for the kind words. Thanks for having us, and thanks for organizing this great event. So yeah, we'll get straight into it. So I'll be telling you today a bit more about who we are as HTL Technologies, as well as what 3D construction printing technology currently stands at within Ireland. So firstly, to start off with is what is HTL and who are we and what do we do? So HTL is a construction technology company that provides certainty in projects through automation and technology. So we're essentially 3D construction printing service providers, as well as equipment manufacturing, distributors. So we exclusively use cobot technology. So cobot is a Danish company who manufactures the 3D printers that we use, which you will see a bit later on in the presentation. So we essentially distribute their technology within Ireland and the northern part of UK, and we use their technology and their equipment to provide and to deliver our projects. So why do we use 3D construction printing? So we use it due to essentially leveraging new technology. As we all might know, the construction industry has been stagnating with developments through technological developments over the past couple of years. So we saw that sort of that opportunity to apply this technology in the construction industry. And I'll show you throughout this presentation why we do it and what we gain from using this technology. So the most important and the most sort of rudimentary advantages we get from this technology is time savings. We spend less time on site, which leads to cost savings. Time is money. If you save time, you save money. And by that, we increase the value that we provide on site. So where do we fit in then with this technology? So we are categorized in category 4 of the 7 categories of modern methods of construction. And as you might know, most of the modern methods of construction currently is mostly based on on-site production or on-site assembly, so it'll be off-site essentially manufacturing, which will then put it on a mode of transport, transport it to site and assemble on site. Whereas we sort of have the advantage of doing it both off-site as well as on-site. So we can essentially set up our gantry system printer on an indoor sort of factory-like setting where we can essentially print components, transport it to site and assemble. But where we sort of mostly do most of our business and where we see it sort of the most benefits of it is by actually taking our 3D printers and the gantry system, installing it on site, and we call it essentially taking the digital model directly on site. So we have a factory essentially taking it to site instead of having a factory transporting it and then assembling. So essentially, due to the digital nature of this technology, we essentially then take our digital model directly from our CAD model. It gets transported essentially in a G code, which is coordinates that the printer reads, which is a path that it follows, which then directly gets placed layer by layer on site. And with the shorter construction timelines and the efficiency of movement of this machinery and equipment, that leads us to shorter construction timelines, and that ultimately leads us to an increase in housing delivery. which is essentially where we place most of our focus on, is on social housing development and social housing delivery. So then what is this problem that we're trying to solve? So with essentially the ever-increasing demand in housing demand and an ever-decreasing skilled labor force, that leaves you with a stagnated supply chain. And that's sort of where we then come in, where we aim to use this digital 3D construction printing technology to ramp up the rate of production by churning out products and housing at a faster rate to meet the ever increasing demand. And we can do this essentially with a very low skilled labor force and a lot less people on site. So then what's the reason why we implement this technology essentially is firstly is due to speed and the amount of output we can get from it. So we are about 25 to 30% shorter on site during the entire construction timeline. And that essentially is just due to the speed at what the machine travels at. So we can print essentially up to 250 millimeters per second, which is, it sounds pretty slow, but it's actually very fast, which leads us to do about 1.5 to 2 meters of vertical rise per day. And with this, we can complete around 80 superstructures per annum per machine. And that is if the machine is based on delivering a terrace of 4 units. So the machine size would then ultimately be scaled to fit the project's brief. So you'll see later as well, I'll talk about what the machine setup looks like. It's essentially the machine can be scaled towards the project suitability. So if it's a small scale project, the machine can be reduced in size. Where it's a large scale project, the machine modules can be added to it to essentially fit the description of the project, which is why it's a fully modular system. So you can add components and remove components. And then with the speed as well, and essentially harnessing the digital nature of this technology that leads us to reduce labor, we can operate the machine with roughly 3 to 4 operators per machine. So I'll run through essentially the labor requirements a bit later on, but essentially with 3 people on site, you can seamlessly run this machine without any issues, which is around 40 to 50% more efficient use of labor compared to a traditional masonry constructed project. And with this as well, we are leveraging technology and digitization, which leads us to extreme accuracy and reliability, because we're essentially transferring directly our BIM and our digital model directly to site. So that leads us to around 5% or 5 millimeters of tolerance over around 5 to 10 meter spans. And what that essentially opens doors for us is prefabricating most of the components. So once the design is freeze and all of the stakeholders are happy with the design, we can essentially then prefabricate all of our components, our windows, our doors, our internal partitions, our timber roof trusses, etc. We can send them to the manufacturers and tell them to exactly manufacture according to those design drawings and when it needs to arrive on site. So that essentially gives us a just-in-time delivery process where that exceptionally reduces the amount of time spent on site. And that's something we tested through doing R&D projects, as well as we recently completed the first social housing scheme in Ireland for Louth County Council, which is where we as well prefabricated all of the components and set a date for the manufacturers to deliver on site. And the material that we're using to construct with this technology is traditional or very, very close to traditional ready-mix concrete. So with that, we know the quality of concrete. It has more than 100-year plus design life cycle. It is the concrete that we're using. We're essentially comparing it to a block manufacturing and block placement on site. So compared to a traditional block that is currently used, it's between 8.5 to 14 MPa. And the strength we get from our concrete is 50 MPa. So we're roughly 5 times stronger compared to traditional methodologies. And I mentioned the 5 mil tolerance compared to the traditional 20 millimeters, which allows us then, to prefabricate most of our components. And with the concrete that we use, concrete is inherently fire resistant due to its properties. So that saves a lot in the fire, essentially, the fire output and the works have to go into the building to get it fireproof. And as well as concrete is very dense, so that gives you good acoustics within the structure. And then in terms of sustainability, what's a great advantage about this technology as well is essentially the ability to place material only where it needs to be. So inside of our BIM models and our designs, we have our openings for our windows and our doors. So that essentially the printer knows, it's smart enough to see, okay, that's a gap in the superstructure. So it would essentially pass through the opening without extruding material, which is essentially, that's gives you that accuracy and the waste reduction in terms of that. We're currently focusing on a cavity wall construction, which is tied by wall ties for stability. But we're currently working on a new detail, which will be comparable with timber frame in terms of carbon embodiment. So we're aiming on reducing the cement content in our mix designs for the material that we use. But as it stands at the moment, we currently have the lowest carbon embodied 3D printable concrete that exists currently. And in terms of the material, then again, due to the high density of our material, we can use the thermal mass to essentially heat and cool the building. So we rely less on external heating and cooling to cool or heat up our buildings. And then we've done air tightness tests on our buildings that we have printed. And without any air tightness membrane, apart from the ceilings and around the window openings and door openings, we already exceed passive grade air tightness on our material. And then with all of this in mind, we essentially can give you project certainty by delivering on time, on budget, whilst delivering value. And then with that all keeping in mind, we can save around 5 to 10% on the total cost per home. So then just a general overview of how the printing process works. So it essentially starts with your CAD and your BIM design. So that's traditional to any sort of building methodology at the moment. You'll design it on CAD or Revit. From that, you'll then export your file into a step file, which is essentially just an export file, which is then put into a slicer software. So a slicer software is essentially a software where you put your step file in, you give your building parameters such as layer width and layer heights, as well as printing speeds. What that then essentially does is it takes your entire building, it slices it up into layers, which is then generating code, which we call G code. And that's essentially X, Y, and Z coordinates that we put into the printer's brain, if you call it like that. And that then extrudes material according to those coordinates and then builds up your structure layer by layer. And then in terms of the material delivery, we partnered with Roadstone to develop this ready-mix concrete material. So how it essentially works is the material would arrive on site in the ready-mix truck. We would check it for the consistency by doing a slump test. And then as soon as we're happy with the consistency of the material, we have a concrete piston pump. It transfers the material from the truck into the pump's hopper, which then pumps it through a series of concrete hoses into our printhead, where we finally dose it with an accelerator to essentially accelerate the hydration process of the material, and that then builds up your structure layer by layer. So and then in terms of the equipment that we use, so like I mentioned, we use cobot technology, and it's a gantry frame. So it essentially means it has X-axis, Z-axis, and Y-axis. So it's essentially your width, your length, and your height. So like I mentioned as well, it's fully modular, so you can scale it exactly according to the requirements for the project. So if you're looking at small scale, sort of lab scale testing projects, you would use a 2-2-2, and the twos essentially mean how many modules are on each axis. And the modules are 2.5 meters each in length. So the larger the project, the longer and the more modules you need to add. So essentially for the project that we completed in Dundalk recently, we used a BOD 594, which is essentially 12.5 meters in width, 19 meters in length, and around 10 meters in height. So with that, we can achieve a story of up or a 3-story building essentially. And then in terms of personnel requirement, like I mentioned, you need around 3 to 4 people on site. So the most important person on site would be your print operator. That's the person who controls the movement of the printer and how much material is extruded. So essentially, he would be the one that generates the slice files and the print files, loads it onto the printer, and operates the printer. So essentially, if the printer needs to speed up or slow down, he's the one that controls that, as well as how much material should be extruded or if the material extrusion should be reduced. And that's essentially how much material is deposited out of the end of the print bed. Then secondly would be someone that helps on site, which we would call a print assistant or a material assistant. So that's just a general laborer around site. So with the cavity wall construction that we currently employ, that would essentially entail of placing wall ties, etc. And then you have a pump operator. So the person who is on the piston pump, ensuring that the material is constantly fed into the pump and that the material that comes out of the hopper or out of the ready mix truck is still adequate for printing purposes. And then we've removed the material operator due to us using ready mix concrete. So previously it would have been done by essentially batching concrete on site with a mini batch plant. So that is essentially, we've mitigated or removed that completely from site due to essentially the volume output we can get from it. So with the batch plant, we would normally get around a volume output of around 1 cubic meter per hour, whereas with the ready mix, we can currently get up to 4 cubic meters an hour volume output. So it just makes sense in terms of scalability and speed of construction to remove that from site. And then in terms of certification of your material, each time that batch plant would move from site to site, you would have to get it recertified. Whereas we have the ready mix trucks arriving on site, Roadstone is NSI certified and provides EN 206 compliant material arriving on site. So we essentially remove that obstacle out of the way by getting material from already a factory production controlled material provider. And then in terms of material, so it's a fully EN 206 compliant material. So what it consists out of essentially is 99% of locally sourced materials, which would essentially be your cement, your aggregate, and your water. And it has 1% of admixtures. And the printing material is, in a sense, a very interesting consistency, as it essentially has to be flowable enough to be pumped through all of your concrete hoses. But as soon as it's extruded, it should also be stiff enough to hold its shape and also hold the weight of the following layers that's placed on top of it. So then the admixtures that we use for this is essentially a retarder within the ready mix truck. So that essentially just allows us an open time of around 8 hours on our mix, which gives you around a full day with a mix without the material setting. And then we also have plasticizers and super plasticizers, which essentially gives us the flowability that we need. And then we add an accelerator at the print head, which is essentially just to accelerate the hydration process. So as soon as the material is deposited, the hydration process starts. And there's also an optional stiffener or a VMA, a viscosity modifying agent, which you can add at the print head or you can add in the truck already. So we've done a bit of testing, and the best way we found to implement it is to add it already in the batch plant. So while the mix is being batched, at the batch plant, we already add that viscosity modifying agent. And then we've done a series of tests then to verify essentially that our cube casted or mold casted cubes for compressive strength at the batch plant and the lab environment is the same as the material that's extruded at the end of our nozzle. So we've done a series of tests to essentially prove that. And from the tests that we have done, we can conclude essentially that the printing process does not affect the material properties, as we still surpass our concrete specification even after the printing process. Then in terms of regulations, how we got through the regulations is we design and comply everything with building regulations from part A to M. And then the load that is placed on the structure is essentially obtained from Eurocode 1. So that's the load placed on the structure. From a materials perspective, like I mentioned, we receive our materials fully EN 206 compliant and NSAI certified from Roadstone. And then there's essentially two ways that we could have gone about designing the structure. So of what most people do currently in the industry is they use a different material. It's not concrete. It's a mortar material. So that essentially means it's concrete minus your coarse aggregate. So we essentially, when we looked at the scalability of this technology, we asked ourselves, would this be feasible from a cost perspective if we use mortar to print the buildings? And then we essentially came to the conclusion that it would not be, for the main reason that mortar is around 10 times more expensive than what concrete is. And that's due to essentially the constituents of the mix. So what it consists of is essentially a very high cement content and a load of dried components. So everything is essentially pre-batched and dried fully and arrives in bags. And then you make your material from that. So that also means that if we're in Ireland and the material that we're using is manufactured in Germany, we'd have to ship over that material from Germany and then make it here, which doesn't make sense in terms of cost and in terms of carbon embodiment. So then how they design is according to Eurocode 2. So they would essentially design a reinforced concrete structure. So they'll essentially print permanent formwork within their walls and backfill it with rebar and structural concrete, and that takes the load off the structure. Whereas we using fully compliant EN 206 concrete, we design according to Eurocode 6, which is the masonry standard, which allows us to place all of the weights and all of the load on our actual 3D printed concrete. So that made a lot of sense to us that we actually have a functioning printed material. It actually carries the load of the structure, whereas it's just essentially a facade, as well as being more carbon efficient, as well as cheaper. And then in terms of execution, it is following the relevant standards in terms of workmanship and execution on site. And there's a new ISO ASTM standard specifically for additive manufacturing for construction. It has been adopted by NSAI in December of 2023. And that's essentially qualification principles and quality control procedures that goes into additive manufacturing for structural and infrastructure elements. And we are happy to say that we were essentially the first ones to implement the standard worldwide, and we implemented it for our social housing scheme we completed in Dundalk, and we're very happy to say that we are fully compliant with the standards in terms of all of the regulations and setouts according to that. So then essentially how our design details look like according to Eurocode 6. So if we start from the bottom going up, it starts off with a traditional strip foundation that is dug out and cast on site. We then utilize prefabricated rising walls, which is then backfilled with your stone fill and your blinding layers. On top of that, we utilize a prefabricated concrete slab, which is already insulated. So essentially that arrives with the precast rising walls on site. And then only after that, we would bring our printer to site and start installing it. And then in terms of installation time, it takes about 2 days to assemble the machine. So it would arrive on a truck and it would be offloaded with a mobile crane. So it's a day for assembling the gantry, and then it would be a day to calibrate and plug in all of your wires and get it ready for printing. And then once the project is complete, it would be a day then to break down the printer and transport it away from site. So then in terms of what our details look like, we use a cavity wall detail, which is essentially 200mm concrete leaves of 3D printed concrete, which is then essentially after the project is, or after the superstructure is completed, we would drill in and pump it with an A2 fire rated flowable insulation. So that essentially gets us our fire compartmentalization between units. So we don't need any fire socks in between the party walls. And then on the inside, we don't print any of the interior walls. We could do it, but we don't see the benefit of it due to the high strength of our material. It's not, it wouldn't have any purpose if you print the internal walls. So we use essentially partitions in between. It could be light gauge steel, or it could be timber partitions. So then after we print the superstructure, the partitions would be brought to site and installed. And then in terms of the wall configuration, we use a gyp liner frame, which essentially houses plasterboard, and all of our services run behind the plasterboard, so we don't have to chase or drill into any of the walls to essentially have our services there. And then in terms of the flooring, we use traditional LGS or posi joist. So we would use a joist hanger along with a joist, which will form our floor makeup. And then we use traditional sills, concrete sills, and concrete lintels to make our lintels and our sills. It could also be prefabricated steel and passive sills. And then the roof configuration is essentially just prefabricated timber roof trusses that we employ. Then I'll show you just a video of sort of the sequence of how it goes together. So it'll essentially be to start off with the rising walls and do the backfill of the backfill and the blinding. Then the prefabricated slabs arrive on site, and then we start printing essentially. So we do a step PPC detail and insulation detail. That would be essentially our phase 1 detail or phase 1 print. From there, we then go from that level up to our sill level. From sill, it would go up to lintels. We would place our lintels, and essentially we can just print straight over it. From our lintel level, we then go up to our floor level. So you can either place the floors in between, or you can finish the entire superstructure and then place the floors afterwards. We find it a bit easier on placing the floors directly when it needs to be placed. We have tested both methodologies and just find that works easier for us. And then as soon as the superstructure is complete, the internal partitions would come in. It'll be lifted in with a mobile crane or the teleporter, and that will form your partitions. In terms of the party wall, we print a hipped roof. That's just more efficient for our technology. So we use a hipped roof, and in between the units, we use a spandrel panel to form our roof essentially at the party wall section. So if we would do a gable end, we would essentially print up to the hip level essentially, so up to eaves, and then we could use spandrel panels to form your gables. So this is the video that I'm going to show you now, is essentially our demonstration building that we did in Drawda. So this was the first printed building in Ireland, as well as the first ready-mix printed building worldwide. So we're very proud that in between ourselves and Roadstone and our partners in Drawda, that we've completed the very first ready-mix printed building worldwide. So then essentially how it works, after the printer has been set up, the concrete arrives on site. We check it for the right consistency. Then we essentially start printing. So you'll see it built up layer by layer, and you can program into your file where you want openings to be. And then the printer will essentially leave that opening there. But what's important then, for those openings, you would need some sort of support if it prints on top of it. So in terms of the lintels, you would essentially need, if you leave an opening for a socket in your wall, you would have to have a lintel there to just carry the weight of the following layers. And for this, we used a prefabricated floor cassette, which was essentially just lifted in and placed into position, as well as the LGS floor partitions. And then we did two units. The one unit on the left-hand side, we left completely raw, so that it's essentially a show unit, so that when you step inside of the left-hand unit, you can see the wall built up and how, you know, the layers form the building. And then the right-hand unit, we fully kitted out and fully fitted out as a regular spec social housing unit in Ireland. So there you'll see the slabbing on the walls and the stud partitions. We apply a single coat render on the outside. And then there's essentially what you'll see what the inside looks like. It just looks a very high spec social housing unit. And this was essentially a scaled down version of our actual project that we did in Dundalk now recently, which was a terrace of 3 houses. And there's all of our project delivery partners as well. And then there's essentially just a photo of the completed house, of what it looked like after it's been completed, and some interior shots. So that would be your living room, your kitchen, and that's essentially the spec of what it would look like. So then in terms of the carbon of the material that we use, so concrete generally has a bad rap in terms of carbon embodiment. Everyone thinks concrete is a very bad material, but that's essentially just due to the volume it's being used in. So concrete is the second most used material in the world, the second most consumed material in the world after water. So that's essentially why it has such a high carbon embodiment. So there was a study done by Arup, which essentially takes the same footprint of a building and then compares various different building methodologies to it. So this, what you see is essentially a graph of comparative building methodologies on the same footprint of a building, which is essentially the kilograms of carbon dioxide emissions per square meters of GIA. So if we then essentially compare ourselves, we are essentially at the moment, we are the light green bar, second to the left. So that's essentially where the concrete that we currently have falls into place compared to essentially cavity wall construction with concrete blocks, which is the gray one, as well as cast in situ concrete or concrete block construction, the 3 in the middle that are the highest in embodied carbon. So then if we look at essentially timber frame construction, which is the dark green second from right, that's essentially our target where we want to get to. So essentially we are in the development of a new construction detail, which will allow us to improve the embodied carbon of our material and reduce the amount of material that we use in building the superstructure. So at the moment, we are sort of in the beginning phases of that. So where we currently sort of streamlining to go would be HTL design phase 2, which is the third one from the left-hand side. So we're almost getting similar to timber frame levels of carbon embodiment. And then if we essentially deviate from the existing regulations, which would mean we would get an AgriMOS cert for what we aim to do, we predict that we can get close to and less than the carbon embodiment of timber frame currently. So that's essentially what we see in terms of the future on the material development that we do and the design details that we're trying to use. So that then brings me to the project we recently completed in Dundalk. So it was a terrace of 3 social housing scheme we completed for Louth County Council. And essentially what it was is a terrace of 3 3-bed homes over 2 floors. And it has a total square footprint of around 330 square meters. So essentially it's exactly what the social housing regulations are in terms of size, what it should be. So like I mentioned, this technology is very free form. If you do a straight line or you do a curved line, it's going to be exactly the same cost. So this design is not going to win any architectural awards, but we're essentially just focusing here on maximizing the output and the speed of construction and sticking to the existing social housing scheme sort of design guidelines. And then in terms of printing time for this project, it was fully completed in 12 days. then the superstructure was complete. With printer setup and takedown, the construction timeline that the printer was on site was roughly 15 days. And like I mentioned, it's fully load-bearing structural concrete, and it's EN 206 compliant, delivered by Roadstone to site, fully BCAR compliant, and it has a NZEB accreditation of A2 as well. We could get down to A1 and passive levels if we install PV as well, but currently we're at A2 level on the BER ratings. And then it was essentially printed in 7 sequential phases. So if we start in, like I mentioned, from the rising wall, we go up to our DPC level. We would then install our step DPC as well as our DPC. From DPC, we go up to our sill level. We would then essentially have styrofoam placeholders we put into place, which essentially keeps the space we require for the sills to be installed in afterwards. From there, we would then go up to our lintel level. For this, we use prefabricated concrete lintels. They essentially, we just slot them into place. We print straight over them. There's no issue in that. From there, we go then to our floor level, our first floor level. It is then essentially the joist hangers as well as joists are placed. From there, we then go to first floor sills, first floor lintels, and then eaves. So it's a 7 sequential phases, where after the superstructure is complete, we remove the printer from the site and the rest of the works commence on site. So we essentially have a main contractor that's responsible for this. We then come in as specialized subcontractors. We complete the superstructure and we remove the printer from site. So essentially all of the work that carry on after us are traditional at the moment. There is a lot of room for improvement, which would essentially streamline the entire process again, shortening the construction timelines. But there's a lot of testing that still needs to be involved in that. But we are essentially open to work with any MMC provider as well. And like I mentioned, the extreme accuracy, we can essentially just then prefabricate all of the components and slot it into the building. So there's essentially a small little video of how the nozzle extrudes the concrete. So that was printed on the first floor, and then in between we'll see the wall side there, that tie the walls together as well, with the ready mix truck there on the right hand side as well. But then there's just a short little video of the project as well, how it went. So essentially it started on site with breaking ground and casting the strip footings, where after that was complete, the groundworks were completed, the rising walls were brought to site, as well as the prefabricated insulated slabs. We then, after that, we brought our printer to site, set up in 2 days. So there's a mobile crane arriving. We set it up with the mobile crane, took a day, second day just to calibrate the printer, and then we started printing. And then 12 days after, we disassembled the printer again, and that superstructure complete. So there's us printing onto essentially the DPC. You'll see most of the corners or the main corners of the house are round. And the main reasoning for that is essentially just due to efficiency. It is possible to do square corners as well. It is just a lot more efficient if the printer moves in a circular path around the corners. So that gets us the speed as well. And then you'll see, I don't know if you saw there on the nozzle, it has an extension flap. So that flap essentially acts as a smoothing plate. So as it moves around the building, it skims off essentially any excess concrete from the layers, which gets you a smooth finish, which is essentially better for then coming afterwards with the plastering. There you'll see the joist hangers being placed as well, and we can essentially just sprint straight over them with just lifting up the nozzle slightly during that phase. And then those mesh that we place is essentially just mesh reinforcing to give the concrete a bit of tensile resistance in the fresh state to avoid any cracks from occurring. And then afterwards, the same procedure as what happened in the demo house. The roof trusses were lifted, partitions were lifted, and then the rest of the internal work commenced. So that's the current state of what it's at, and it's due for completion in about 6 weeks. So end of October, the first ground was broken on site in June. So it'll be around a 5-month total construction timeline. And then what we predict we can do with the houses annually, if we employ 12 machines with around 3 to 4 operatives per machine, we can do roughly 1,000 superstructures per annum. And then the key performance indicators during this project, we were printing roughly at speeds between 150 to 230 millimeters per second, which gave us a volumetric output of 3.5 to 4.5 cubic meters per hour of concrete. And that essentially translates into a vertical gain of roughly around 300 to 400 millimeters of vertical gain per hour. Like I said as well, using ready-mix concrete, we're roughly 5 times stronger than traditional masonry that it essentially replaces. And it's the lowest carbon-embodied 3D printable mix that currently exists, saving up to 278 kilograms CO2 per cubic meter that is placed on site. And as well, it's a fully load-bearing structural concrete mix supplied by Roadstone, which is fully compliant with Eurocode 6 and EN206 standards and the building regulations. And very important as well, it was the first 2-story 3D printed building in the world to utilize EN206 compliant ready-mix concrete. And then just some different applications. I'll quickly run through this because we're a bit short on time. But it's essentially what we did, sort of a model that we did, which would be for student accommodation. It'll essentially be 2 blocks of student accommodation, which is essentially you need space to bring out down your printhead at the end of the day for cleaning. So if we want to yield the maximum amount of area on our print area, we need to essentially make all of the space usable. So what's nice about this is we can bring our printer down in the middle of the 2 units at the end of the day. And that will then, after the superstructures were complete, that would essentially act as a staircase to connect the units in between. So there's no wasted space in this. And essentially this would be around 16 print days per block. And 48 apartments we get from it. It's a high density, sort of low volume construction, which is very fitting towards this technology. And there's just a render of sort of what it's going to look like, or what we envision it to look like, and there as well. And then another one as well is we submitted this for an RIAI competition for an infill site in Sligo, which is again high density, sort of an application for this technology, which would be a total of 21 units over 2 stories and 3 stories, and a total program duration of around 20 months. And they're just some renderings again of what it would look like. And then so the technology currently is mostly used for housing applications. So there's some examples of projects that have been executed around the world currently. It's as well very useful for infrastructure elements. So they're using it for water attenuation tanks as well as wind turbine bases. What really makes it then stand out in terms of the wind turbine bases, currently the bases are restricted to transport limitations and fitting onto the back of a truck. So that makes it very small because it needs to fit below bridges and be on rail transport and road transport. Whereas if you essentially take the printer to site and print it on site, you can get up to 25 meters and a very wide base from your foundation, which essentially then yields more energy efficiency out of it because you can then go taller, which catches more wind and generates more electricity. And then in terms of the water attenuation tanks, so as we all would know, the pressure would increase with depth. So the pressure at the bottom would be more than the pressure at the top. And if we cast water attenuation tanks traditionally, we sort of restrict it to uniform width from top to bottom. But if we print it, we can essentially alter and taper up the width as we go from bottom to top, which leads to roughly 20% savings on materials for the same features. And then there's numerous different applications again for printing staircases, bridges, bridge decks, etc. It's very widely used for architectural applications, urban furniture, for example, and the likes of bus shelters. And then finally, I close off then with the training. So it's very important to essentially roll out training for this, because we can't scale up if there's no operatives that's actually operating these machinery. So we work alongside with Louth County Council, LMETB, and AMTCE, where we provide training on this technology, essentially in terms of a 2-day training. So we'll give, the first day would be a theory-based training, where we essentially give a history and sort of more in-depth knowledge of what the technology looks like, how it works, what materials properties are required, and how to essentially an introduction on operating the machinery. And then the second day would essentially be then a live print, where you go to our R&D facility and see everything that's involved from startup to actually printing, from designing and implementing it as a printable file. And then we're in the works as well as developing a sort of a 2-week training course, where we would then operate and train the attendees to fully operate the machinery. And that's very important for scaling this technology, as we would need operators in the future. So thanks very much, and we welcome any questions.
Thank you very much for that, Jandré. It's a very impressive presentation. It truly looks like it's the future of housing. Your slides are of excellent colourful quality, and videos that give us a real feeling of the printing in action, which is great for us to see. So we have a number of questions in already, but just before I get into those, I might remind you to type any questions into the question and answer section and not the chat box. So as I say, we've a lot of questions in there. So to get started, question from Brian: if these houses are to be in warmer, sunnier climates, how will the material react to constant direct sunlight and regular heating and cooling cycles?
Yeah, so it's traditional concrete. The only thing that changes is the way that the material is placed. So instead of casting it from a hopper from a crane, we essentially just extruding it from the end of a printhead. And then the sort of your R values and your insulation properties, the cavity width can be essentially tapered to meet the R value that you require and the lambda value you need. So if you want it to be more insulated, you just increase your cavity width. If you want it to be less, you can reduce it. So it's, in terms of that, it's essentially just the same as mass poured concrete. And then on the outside, we apply that render coat as well, which is breathable as well.
Excellent. Then we have a question from Patrick: how are the 3G concrete printers powered? And as well as that, the associated computer, IT and CAD stuff. And is it a single independent power supply? And can it be done using a generator?
Yeah. So on site, we use a 45 kVA generator. The printer itself actually uses almost no power. So it would be essentially, it takes 1 kVA to run the printer. The thing that takes most of the energy supply is essentially the pump. So the pump is very energy intensive in a sense, due to having to pump a load of volumetric concrete up 150 meter lines in terms of the line length, and up around 5 meters up in the air. So that's what takes the most power. And then in terms of the computers, I print essentially on site. We would use an iPad. So you control the printer through a static IP address. So then I can essentially just use an iPad to control it, which is just empowered by a power bank.
That's not going to use much power there, all right? Then Andrew, question here: what about inclement weather? And I know we've had this, someone else has asked this question as well. Rain, snow, frost, etc. How is the manufacturing and concrete placement affected by that, if at all?
Yeah, so the placement, essentially, it has to follow the EN standards as well. So 3 degrees and falling, we can't place the concrete. So that's just standard practice as well. And then in terms of inclement weather, we can essentially print in moderate wind and rain. So up to 35 degrees Celsius, we can print up to, which would probably never happen in Ireland. So we're safe in that regard. And then in terms of rain, we can print in moderate rain. So if it starts to rain heavily all of a sudden while we're busy printing, we prepare a set of DPCs that is cut according to our wall dimensions. So if it starts to rain, we essentially just place the DPC over the layers. And then as the printer moves along, we would take it away, it'll print, we'll place it back. So that essentially just stops the water from penetrating too deep into the surface and essentially changing your water to cement ratio of your mix.
Okay. And then Paul has asked a question here. Why is the wall designed to EC6? Would EC2 plain unreinforced concrete approach not be more relevant?
Yeah. So it could be designed as both. The reason we designed to Eurocode 6 is essentially to take away any rebar. So we don't need any rebar in our current design. We can place all of the structural load on our printed concrete. If you design according to Eurocode 6, because printed concrete doesn't have its own design standard or design code, you have to essentially rely on permanent formwork. So basically, when you print your cavity wall, you print a permanent formwork on the inside. That'll be filled with a rebar cage and structural concrete. So that takes the load. So your printed concrete doesn't take any of the load. So that's the reason why we went for Eurocode 6, which is essentially to place the load on our structure.
Okay. And then Santosh has asked the magic question, Solus, what was the cost of completing the building? And what's meant by that is what it costed the investor for the 3D design building that you showed in the video.
Yeah. So I can't give you the complete cost. I don't know that myself, but essentially we cost comparative to block construction. So in terms of using the technology, and the equipment is quite expensive. So essentially you need that investment in the machinery. So in terms of the material that we use and getting the equipment to site, we're a bit more expensive than traditional at the moment. But because we're saving time on site, we're saving the money as well from the contract price. We essentially come to the same price as what traditional block construction is currently being constructed for. So we're not cheaper, but we're also not more expensive at the moment. And I think it's a very good thing that the technology is still at its infancy. There's still a lot of room for competitors to enter the market, more companies to do this, which will drive down the prices. So at the moment we're comparative, but I think it's going to be cheaper in the very near future, the more this technology is being utilized.
Thanks. Salima has asked how the concrete curing is done on these projects.
So essentially, after the print, we would spray a curing compound onto the surface, which is essentially, it creates a wax-like surface on the surface of the concrete. So that essentially traps the water into the mix. So it doesn't allow the water to evaporate and it to shrink. So that stops it from cracking. And we introduce fibers into the mix. So it's a polypropylene fiber that's into the mix design, which also gives us a little bit better durability. And as you probably would have seen during the video, we place like a steel mesh on the layers as well. So above windows and below windows, we place that steel mesh. And that gives it that tensile resistance as well to the material in the fresh state. So when it has the tendency to shrink, it'll give that little bit more resistance to just stop it from shrinking excessively and stops cracks essentially from occurring. Curing, we spray water and we spray a curing compound afterwards. And then in between trucks, so essentially if we print a print day, we'd essentially do roughly 14 cubic meters per day. So we'll order 2 trucks of 7 cubic meters, one in the morning, one in the afternoon. So in between trucks, we would have a water like a backpack sprayer with water, which will spray onto the layers, just to keep the environment moist, and to keep the water within the material.
Or you might get an old shower of rain that'll help as well to do that, the way things are lately.
That's normally the case.
David is asking here, are the separating walls between units printed?
Yeah. So we print the party walls between the units, yes.
Yeah.
It's just the internal walls that we don't print.
Yeah. And then Seamus is asking, oh, sorry, no, it's the same again, but the weather, do you need to adjust? Oh, yeah, so there's a question here from Sean. Do you need to adjust the mix additives for changing weather conditions on site?
Yeah. So basically, the accelerator dosage is very dependent on your print speed as well as the environmental conditions. So if we print faster, that essentially means we need to dose more accelerator, just essentially because we're increasing the volume of material that we're extruding. So we need to increase the amount of accelerator. If it's colder, we also might need to increase the accelerator just because the concrete takes longer to set in colder conditions. So there's two ways we can do it. We can essentially increase the accelerator dosage, or we can print slower. So that's essentially our two options that we have. So obviously we have a range of permissible accelerated dosage that we can do to essentially avoid the concrete having an overdose of accelerator. So yeah, we have this permissible range. If we exit that or go above that essentially means we can't increase it anymore. We then just have to print slower, essentially. But that's not it doesn't occur a lot. It's a very sort of if we start with the specific percentage at the start of the day, we normally just stick to it. So it doesn't change, it's not very sensitive to change.
Okay. And so I skipped over Seamus's question here because I saw about heavy rain. So what he was asking here is the operation weather dependent, high winds, heavy rain? So just in relation to the winds, does that affect?
Yeah. So the winds, we can go up to printing in 45 kilometers per hour winds. Apart from that, we need to stop printing. So generally, the wind doesn't affect it. Weather dependency, like I mentioned as well, we can print in moderate rain as well. Heavy rain is where we then pull out the DPCs to protect the material, but that would be sort of a last resort. If it's heavy rain from the start of the day and we see there's no chance of it really getting a bit lighter, we would just call off the print for the day.
And we have a question here from John O'Connor, one of our committee members. In overall terms, what is the time saving on the whole building construction, not just the 3D walls, in comparison with traditional building?
Yeah, so we did a program analysis on the project that we completed now. With it being built by block, it would have been 8 months on the total duration of the construction timeline. And with us now printing it, it's 5 months. So it's on this project that we have empirical data on, we saved 3 months in terms of the construction timeline. And that's not just the walls, that's from start breaking ground, printing the walls, getting all of the finishes internally, externally done, until handing over the keys. So it was a 3-month save on the construction timeline.
Excellent. And Santosh is just asking, just in relation to cost again, the main question is, can you compare the cost between normal precast building and 3D printed building, just in terms of a percentage, and what are the disadvantages or challenges compared to a normal reinforced concrete building?
Yeah, so the cost-wise, it would probably be a bit more expensive than normal precast buildings. But the advantage then that we have is design freeform. So we don't need any formwork for it. We can essentially create any shape then by just stacking these layers on top of each other and just following the code that we design. So it's very simple to change your design. It's essentially just a line on your CAD drawing that you change. And then, it's 5 minutes of your time. you don't have to go change formwork or make new formwork. So that's sort of the advantage then compared to traditional cast concrete. Disadvantages, it would probably be it's not as great in transporting. So that's why we prefer taking the sprinter to site and not sort of pre-casting it, then transporting it to site. So because we don't have rebar, it's very difficult to transport walls if we print them off site. So we would specifically need to put in rebar into the printed element, which can be very challenging. That's one of the main challenges of this technology is how do you incorporate reinforcement into it? There are ways of doing it. You can essentially print a formwork, then put in a rebar cage and backfill it with concrete. So that's one way of doing it. But yeah, that's definitely one of the main challenges and disadvantages compared to normal reinforced buildings is how do you know, the difficulty of adding reinforcement.
Excellent, very comprehensive answer, Jandré. Just a few more questions here for you then, and we'll wrap it up then. We're gone a few minutes after 9 there. Frank is asked, can the method be used on house extensions or only on new built houses?
Yeah. So if there's space on site, it can definitely be used for housing extensions. Yeah.
Okay.
I've seen there's now, just last week, they've printed an extension of a Walmart warehousing unit in the US, where they essentially just put up next to the existing building and print the extension from it.
And then there's another question in relation to cost from Eleanor, but a slightly different question. Is what's the capital cost of the printer for the sizes shown, and what happens if the printer breaks down?
Yeah, so for the prices of the printer, it would obviously depend on the size of it. It ranges from the smaller scale, it's from around 500,000. It can go above $1 million. So it's not cheap, but it's an investment.
Yeah.
And then what happens if the printer breaks down? That's why you need a well-trained and a team that knows what they're doing, essentially. But it's very uncommon that it would break down. You would get parts that break down, but you always have spare parts with you. So for the parts that break down most often, you would essentially you'd have those spare parts handy just to replace it very quickly. The most thing that breaks down in the printer is the software. Well, it sounds like it breaks down very often, but it doesn't. But like the main issue we have is with the software, and Cobot is very good in their customer care. So we have them on speed dial. So if anything happens during the project while we're printing on site, we have them and they will sort out the issue very fast. And what works nice as well is they have operations in the US and Europe and Malaysia, Asia Pacific. So it doesn't matter when you're printing, there's always someone from their team that is accessible.
That's brilliant. So 2 last questions then. So Stephen said here, the examples shown were terraced houses with the same finished floor level. Can the printing manage a terraced or a semi-D block with a stepped finished floor level to suit steeper sites?
Yeah, definitely. Yeah, we're looking at the project now that has different levels in the house. Definitely achievable, yes. If it's on a steep side, you might lose a bit of print space because you have a certain height of print area. And if one leg is higher than the other, your sort of build height is referenced from the lowest leg. You'll lose that distance between the two, essentially in your printable area.
Okay. Kenneth is asking, do you provide crane, turntable, spec, space, and so on?
Yeah, so the space would obviously, it would depend on what size of the printer you use. So we have a fully comprehensive list of how, for each printer size, what's the setup area required and what's the available print area you get from that. And then in terms of crane, the printer components are very light. It's so the heaviest component would be about a ton. So we use normally roughly a 40-ton crane, which is very excessive. But if you go to crane hiring companies, their smallest crane they would normally have in their fleet would be a 40-ton crane. So we normally use a 40-ton crane for setup.
Yeah. Just one last question here then from Santosh. Wants to work in 3D printing and wondering what's the process to get into the 3D printing industry in Dublin.
Get in touch with us.
Well, that might be
Yeah.
might be the answer.
Come to a
Excellent.
training day and then get in touch with us. That would be the best.